Thank you so much for the opportunity to come and chat. That is going to be a tough follow-up on Liz. She's an actual technologist. I am just a product manager, so I get to wave my hands and say that I'm inventing cool stuff, and I have to leave it to people like that to actually do the stuff. I am David Aronchick. I work at Google. I led product management for the Kubernetes project for about 2 years. On behalf of Google, and since then I helped co-create the project called Kubeflow, and I'm here to talk to you a little bit about it today, and really what we're trying to do around machine learning and bring it into the containers and cloud native. So I always like to start with this. A lot of people have a very different understanding of what machine learning is. It's actually an incredibly complicated problem. The idea is, though, everyone overcomplicates it in my mind. The first thing to do is really just start with a question, right? So you say, how much is my house worth? And you might come up with a graph that says, I'm going to say, this is the amount of square footage in my house, and this is the housing price. And you come up with a dot. Maybe you start with your own house. And then you ask all your neighbors what their prices are, and then you ask everyone in your area, or you do a survey or something like that, and now you get a graph, and on that graph you write a line. While dumb people like me just say this is a line, if you want to sound really smart, you say linear regression. This is a linear regression. Makes you sound very, very intelligent. Anyhow, now you have your line, and you answer your question. You say, my house is 2,100 square feet. I should have converted it to meters squared, I'm sorry. And it is $330,000. Fantastic. Obviously not the center of Paris pricing, but you get the idea. But I basically just done machine learning. And congrats, now all you're experts as well. Go ask your boss for a raise. But, of course, the problem is it's never that simple, right? If it was just that easy to do one to the other, everyone would be doing it. You often have things like nonlinear groupings, maybe neighborhoods, maybe there are hills. This one's close to a metro stop. Maybe things are multidimensional. You have lots of different dimensions. We only had 2 dimensions there. Some of the most popular models today might have 100 or more. And things certainly change over time, and you need to adapt to that. And so the way we think about machine learning is, it is a way to solve the problems without explicitly knowing how to create the solution. In this case, for example, we had, here's a square footage, and we're going to draw a direct line to our answer. If you had 100, you might not be sure which specific version, which label, actually resulted in the answer that you were looking for. And to be clear, even the best people in the world face these problems. At Google, we spend an enormous amount of time making sure our data centers run great. Data centers are the very core of our business. They're our #1 expense. And we hire the best engineers in the world to make it renewable, make it highly efficient, make it reliable, all these various things. But when we looked at it, and we looked at all the underlying data, we said, geez, I bet there's something we can do around machine learning here to improve it. The number in data center efficiency is called power usage effectiveness. It's the amount of power you get in versus the amount of cycles you get out. And in our case, the graph looked like this, bouncing up and down. We attached machine learning to it, and it dropped 40%. And then we turned it off to see what would happen, and it came right back. And that's with the best engineers in the world doing all this renewable, all this highly efficient work. We were able to use machine learning without us specifically knowing what the answer was to get this overall improvement. And so you say, machine learning is great. I want to use machine learning. This is fantastic, except machine learning is very, very hard. And it's not just hard because I'm bad at math, it is actually hard. And the problem is something like this. Most folks are over trying to understand, does machine learning apply to them? What problems do I have that machine learning might help? What can I do to adapt my own systems to take advantage of the common machine learning solutions out there? And that's very, very far away from where the story that everyone's being told around machine learning exists. And the reason is because it comes down to basically two things. One, you can try and set up everything yourself. And this is the most common thing that we see. You set up everything from scratch. You specifically have to go and debug everything, figure out what's going on. You have to integrate with your legacy systems. And then when you're finally, got everything up and running in one environment, you then have to spend an enormous amount of time and energy moving it to the next environment where you have a brand new business need. And so it becomes highly non-portable. Or the alternative is you do it using a hosted solution. And in the first 5 minutes, a hosted solution is awesome. You can't believe how fast you're able to get an answer to your problem. Unfortunately, the next 5 years, you have everything that you had on the left-hand side. Highly bespoke, legacy solutions, and you're the exact same amount of lock-in or more, because now you are tied to what that hosted solution is going to give you. And I do want to say, this is not every hosted solution, but certainly the most common situation. So, haven't we heard this story before? I'll give you a hint because you're at a conference called Container Days. The answer is yes. And the answer to that is containers and Kubernetes. Before containers and Kubernetes took hold, everything you just saw there was the exact same before. You might have incredibly locked-in PaaS solution. You might have VM custom building for particular clouds or on-prem. You might have to rewrite your own service discovery orchestration solutions in order to orchestrate those workloads across all those various VMs. Very, very challenging. As containers came in, they gave people a layer of abstraction and packaging around a particular workload, and then you had something like Kubernetes come in that helped orchestrate on top of all of that to give you a declarative way to roll out applications and say, here's what I want you to run, I don't care how, and the system takes care of it. And it wasn't just about running those workloads, it was also about the native extensibility of it. And I think this is something that a lot of people get really overlook. The value of Kubernetes isn't that we knew what was in the box, it was also that we were able to provide you this very clean extension model so you could add new things in without having to fork the code or do any kind of crazy bespoke solutions. And at KubeCon in Austin last year, Chen Goldberg, director of Kubernetes at Google, talked about this and talked about all these various layers. And when we talk about building in a cloud-native way, exactly like Liz was just talking about, using those microservices that are broken down and communicating with each other, we're very proud that Kubernetes supports this natively, where you have all these various layers. From the API to the extension points to the storage layer. Each one of those give you very clean ways to extend and differentiate. And that's what we call cloud native development and cloud native application rollout. And so what we need is cloud native ML. We need the exact same idea to take advantage of the underlying extensibility and frameworks that Kubernetes provides, but build on top of that in a cloud-native way, loosely coupled, microservice-oriented, highly portable, highly expandable. When we think about cloud-native ML, it breaks down to those three key components, composability, portability, and scalability. And to go into each one, the first one is around composability. So when you think about building a model today that answers the question like I talked about at the beginning, everyone thinks about, well, I'm going to use TensorFlow or PyTorch, scikit, maybe I need a convolution layer here and so on. But when you go and talk to data scientists, in fact, that's a very small part of the overall problem. The reality is that there's so much around your machine learning model that really makes the difference on whether or not you're going to efficiently be able to answer your question. From data ingestion, data analysis, transformation, converting things from raw data to giving it some structure and validating it, then splitting it to make sure you're not training on your holdback data and so on. Finally, you get to model training, model validation. You want to do that in a distributed way and take advantage of cloud native features like GPUs, TPUs, and so on. And then finally, rolling it out. You want to roll it out in a production-ready way. Again, just like Liz was talking about earlier, you want to have auditability and make sure that your containers are secure, have knowledge about what's out there so that you can roll it back if there's failures, and logging and monitoring. These are all components that are completely outside the idea of just what model you choose. And the reality is that every business is going to have a slightly different way of approaching it. And so for us, building a solution or thinking about this in a composable way where you can swap in and out individual components is extremely valuable. So now you've taken this and you've built out this great pipeline. How do you move it? And by move, I mean this. Let's say you're building out a single environment for experimentation. These might be just some of the overall elements that you include. All the way down to the hardware, all the way up to model, you're going to have a ton of different things. And that pipeline, that's just the top part of it. You're still going to need everything under the hood. And the reality is, you're not just going to need it in one place. Multi-cloud is the reality. This is from the RightScale State of the Cloud report. And you can see 81% of enterprises are already multi-cloud. And they're not just one cloud. The average enterprise is using almost 5 different clouds. And that means that's 5 different times that they're going to have to take that overall complicated pipeline and move it from place to place. And that is just, you go talk to any IT pro and their head's going to explode around that. For this, it's portability happens very, very natively with machine learning. Very often you have a data scientist who wants to set up an environment locally, and then they'll want to take that, move that to a more productive, faster training cluster, and then finally move it to the cloud for final production. Now, I know what you're saying. That doesn't matter to me. I am one cloud only, et cetera, et cetera. But of course, you are wrong, and I will prove it. How many of you have a laptop? There you are. Congratulations, you're all multi-cloud. And don't just listen to me. Listen to this smart guy, Joe Beda, co-founder of the Kubernetes project. The way I think about it, every difference between dev, staging, and production will eventually result in an outage. Everyone catch that word? Let me just make sure everyone, you see that? Just one more. You got this? There you go. Dev. Dev is an environment. Dev is something you have to keep in sync with everything else. Dev is the reality. Your laptop counts. And that big container over there, experimentation, the vast majority of the time, this is where you are doing your exploration and development and so on. And what happens is data scientists will do that, and then they try and take it to production or even just to training, and they have to rewrite the entire thing. And so what we want to do is help give people the same environment even to their laptop. And then finally, scalability. I touched on this very briefly. You have a situation where data scientists might start in a very specific location, for example, on accelerators, or excuse me, on their local laptop, but then they'll want to accelerate. They'll want GPUs, TPUs, maybe more CPUs or clusters, more disk, even scaling humans. Skill sets around SWEs and data scientists and larger teams and geo-distributed teams. All these are ways of scaling. All right, so that's composability, portability, and scalability. And you, as we said, you know what's really good at these things, containers and Kubernetes, except if you want to use ML on Kubernetes today, you have a lot of work to do. Oops. You got to learn all of these things. And that's not great. And that's certainly not something you want your data scientists spending their time on. And that's why in December of last year, we introduced Kubeflow. It was a brand new project at the time. We were just getting it out there to help people understand how to do machine learning on Kubernetes in a cloud-native way. And at KubeCon, just 1 month ago, we introduced Kubeflow 0.1. And the mission here is to make it easy for everyone to develop, deploy, and manage portable distributed ML on Kubernetes. And so for this, the way to think about it is you start at that base layer, Kubernetes runs everywhere, and then you have your Kubeflow deployment that you describe, and I'll show you how we do this in just a second. And that works on your experimentation cluster, it works on your training cluster, and it works on your cloud cluster. In the box, we have the core to getting a project going today, and I'll demo this in just a second. But best of all is that last line. We use Casenet, which is a Kubernetes native packaging system that lets you customize for whatever you need. Just to start, this is what's in the box today, but our plan is to solve for all of these things. And to be specific, when we say solve, we don't mean that we're going to go and write this stuff ourselves. It means we're going to help those teams that are already writing this software build it out and package it in a way that can be used inside Kubeflow. So let's go to a demo, and we'll show you here. All right. So like I said, the number one thing that people have today is they'll have a common set of problems, and they'll be trying to figure out how to use ML to solve those problems. Here, we're going to use a very standard example, and I apologize, it is a video. Using machine learning, or demoing machine learning is a little bit like watching paint dry. It takes a very long time to get anything done, but this is a very recent recording, and I'm happy to show you what this looks like. To be clear, what we've done here is I'll walk you through the entire process. So this is a very, very common problem. This is called sentiment analysis, where you take blobs of text and you want to make a decision about it. Maybe you're a movie reviewer, maybe you're a restaurant reviewer, maybe you have people commenting in sections, maybe you have an e-commerce site and you want to see what products are getting good versus bad, feedback and so on and so forth. These are hard problems. Google has open sourced a model to do this. It's called Tensor to Tensor, which does a lot of this native language processing. And in this case, what we'll do is we'll take this initial path and we'll say it. So the ramen was awful. It was bland and mushy. Who thinks this is good? Bad? Good? Everyone get it? All right. I think we have mostly bads. But let's see what happens here. We'll go and we will try and predict it. And, that didn't work. So what happened? Well, let's go and actually look at the code. That is not good. Hello? We might have a very brief demo today. All right. Oh. Did I get something? All right, well, that's not good. I'll try and reload it here. Oh. All right, I guess we just had a blank there in the middle. All right, well, I don't know what happened to that middle section, but I'll pass by it. Suffice to say, I think we all agree that the code wasn't working properly. So what we're going to do is we're going to create a Kubeflow deployment, and I'm going to do it right in front of you. The first, we have Minikube installed. For those that don't know, Minikube is a Kubernetes cluster that runs locally on your laptop. And from that, you create an overall namespace that's very, very straightforward. And you download a Kubeflow application. It's very, very straightforward. It's just a skeleton, and it runs fine, right? This is all it is. Once you download that, what you're going to do is you're going to expand and you're going to select a series of applications that you want. So in this case, I'm going to choose 3 packages here. Package 1 is Kubeflow Core. That's just a bunch of set of applications that we think that most people will want. 2, I'm going to include serving, which is actually serves your model. And 3, we're going to include job, which is going to run this broadly. Now, as you can see, I have spaces for adding versions and things like that. I can pin to whatever makes sense for my environment. I'm going to take those packages and I'm going to generate a prototype of that. And the reason I'm generating this is because now I want to fold in a bunch of native variables that are specific to my environment. So now I've created that package, and now I'm going to do one more thing here, which is I'm going to set a local environment and just say, tell Kubeflow, hey, by the way, you're running on Minikube. So make sure to use the right permissions that everything is expecting. And with that, I hit apply Kubeflow, and off it goes. And you can see now, that is literally it. I didn't skip over any steps right there. But what you're going to see right here is the entire environment deploys. Oops. I'm having excellent video challenges today. All right, well, I'll talk about it anyway. What you can see there is an entire set of packages that have deployed out that run all of your applications for you, that are all the machine learning tools that you would need to get something up and running. And one of those tools is a tool called Jupyter. So those that aren't machine learning experts, think of this as Excel, but for machine learning. And in it, you have all these various ways to roll through and make changes, build your models, and so on. On top of that, once you get there, you're able to run and test out your models. Now, the reality is, though, many people will want to use that just for experimentation. But when it comes to actually running distributed workloads, you'll want to do something from the command line. And so in this case, that T to T model, remember what I said earlier, that's tensor to tensor. We're going to use that, and we're actually going to deploy it. And you can see right there, I am creating the tensor to tensor job, and here it is distributed. It created a TensorFlow master, parameter server, and worker in one command. And my goal here is not to run this on my local laptop. You can't get rid of that training cluster. All I'm doing is looking at this application and making sure there are no syntax errors as I spin it up and see if it's running. And so far, it looks great. So I'm happy with it. Now let's go to the cloud. So what I'm going to do next is I already created a Google Container Engine cluster. That's just standard Kubernetes running on top of Google Cloud. And so I'm going to take that. I was originally pointing at Minikube, and now I'm going to point at Google Container Engine. And I'm going to switch that environment variable you saw earlier. I was at Minikube, now I'm on GKE, and I'm saying, okay, please use GKE parameter settings. And now I'm going to deploy Kubeflow. So the exact same thing. You saw exactly what happened there. No code changes. The code that worked on my laptop is now running in the cloud. And that's exactly what we want, right? We want people to have a single deployable artifact that works everywhere. From that, now we're going to kick off a couple of things. Let's kick off that same CPU-based TensorFlow job. I'm going to store it using a cloud-native storage solution. In this case, we're using GCS, but we use whatever your cloud provides. And you can see I was able to kick off that there. And now I'm going to take the exact same code and run it against TPUs. Who knows what a TPU is? Anyone? TPU is Google's native machine learning accelerator. It's what we use internally, and it's very highly performant against a whole number of models. And so on a single Kubernetes cluster, I already kicked off CPU-based training. Now I'm going to kick off GPU-based training. Same cluster, two different types of training. And what you see here, most of all, is that you're able to see an incredible speed up. In this case, you see at the top there, that's the CPU-based training. Let's look at the exact same thing running against TPUs, and you can see it's running almost 100 times faster. Exact same code, exact same cluster, same as I had on my laptop, now running 100 times faster because I'm able to use Kubeflow and the native integration. But unless, just serving a model, just training a model, that's okay. Let's see if we can actually use it. In this case, again, as you saw earlier, I had TensorFlow serving built into the box, and we're just going to spin that up and turn it on. In this case, we use Kubeflow again to build it, and I'm going to go back. Remember, again, this is what we did initially, and now we're going to attach Kubeflow at the top there, and we're going to rerun it, and the model worked correctly. So that really was it. And you saw that was a little bit speeded up. But other than that, that's something you can use for anything. You can take those existing open source models, you can take that existing Kubeflow deployment and roll it out just about anywhere. All right. So I talk a lot. I will try and breeze through the remainder here because I know we're out of time. What you didn't see was bespoke solutions. Everything there was completely open source, nothing tied in natively to the cloud, and you were able to take advantage of cloud features in a completely detached way. Second, cloud-specific, non-portable technology. This was totally portable. The exact same thing that ran there ran in the cloud. And finally, you didn't see me have to fork the Kubernetes APIs. This is the brilliance of Kubernetes. It runs great everywhere. We've had great momentum here. Over 800 commits in the last 6 months, 70 companies are community contributors, 17 companies contributing. And it really is a whole new world. Our goal is to really empower data scientists to change the world in a positive way and help them do that by not having to think about all that infrastructure. In Sweden, they just had a great study where a bunch of data scientists were able to get together and identify just a change in the plowing schedule using big data, just like what you saw up here, to save lives and to prevent injuries. And that's the kind of things that we can help empower. And what I really mean is I want to help give the people not in this room, the real experts for their domains, the ability to change the world. And we need to do that by unlocking all this technology. We are just getting started. Kubeflow 0.2 is due in just a few weeks. It will have even more significantly easier setup. You saw it still having to install CaseNet and other things there. We'll have more Kubernetes native features and more packages, example models, and so on. But best of all, we really want you to tell us. Kubeflow is open. We're very, very excited about the project and really want to hear about your usage and things that you're having trouble with. And you can certainly reach out. We're available in all these various ways. We have weekly community calls, one on European time, one on Asian time. We have Slack, and we're always available on Twitter and email. And with that, thank you very much.